Welcome to this problem walkthrough. Today, we'll be exploring an interesting string manipulation challenge, problem number 1190, reverse substrings between each pair of parentheses. In this problem, our goal is to reverse the substrings enclosed by matching parentheses in a given string. Let's dive in and see how we can solve this step by step. The problem we're solving is to reverse substrings between each pair of parentheses in a given string. The string, denoted as S, is guaranteed to contain only lowercase English letters and balanced parentheses. Our goal is to reverse the contents inside each pair of matching parentheses, starting with the innermost ones first, and then remove the parentheses from the final output. The input is a valid string S, and the output is a transformed string with reversed substrings and no parentheses. Let's look at some examples to understand this better. In the first example, the input string is S equals ABCD. Here, we have just one pair of parentheses that contains the substring ABCD. To solve this, we reverse the contents inside the parentheses, resulting in tba. Once reversed, we remove the parentheses, and the final result becomes tba. In the second example, the input string is S equals you, love, I. Here, we start by identifying the innermost parentheses, which contain the substring love. Reversing love gives us EVOL. We then replace the innermost parentheses, love, with EVOL, transforming the string into you, evilly. Next, we handle the outer parentheses. The substring inside, evilly, is reversed, resulting in ELOVU. After removing the outer parentheses, the final result becomes ELOVU. For the third example, the input is S equals ed, it, oc, l. Just as before, we start with the innermost parentheses, which contain the substring oc. Reversing oc gives us co. Replacing oc with co, the string becomes ed, etco, l. Now, we move to the next set of parentheses. The substring inside, etco, is reversed to oct. Replacing etco with oct, we get edoctile. Finally, the substring inside the outermost parentheses, adoctile, is reversed, resulting in LeetCode. After removing the parentheses, the final output is LeetCode. In the last example, the input is S equals A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q. We begin by handling the innermost parentheses containing M, N, O. Reversing M, N, O gives us O, N, M. Replacing MNO with ONM, the string becomes A, B, C, D, F, G, H, I, J, K, L, O, N, M, P, Q. Next, we reverse the substring inside the outer parentheses, B, C, D, F, G, H, I, J, K, L, O, N, M, P, which produces pnoltjifed. Replacing this with the reverse substring, the string becomes apnoltjigfek. After removing the parentheses, we get the final output apnoltjigfek. To summarize, the constraints ensure the input string is between 1 and 2000 characters long, contains only lowercase letters and balanced parentheses, and handles edge cases like no parentheses, nested parentheses, or empty parentheses efficiently. This structure ensures the problem can be solved systematically for both simple and complex scenarios. To solve this problem, there are several approaches we can consider. First, the brute force approach involves simulating the process of reversing substrings within parentheses. This method works by repeatedly finding the innermost pair of parentheses, reversing the substring inside, and reconstructing the string. While this approach is straightforward, it is highly inefficient because every reconstruction of the string involves copying large portions of it. This results in a time complexity of O(n) squared, where n is the length of the string, and a space complexity of O(n) for intermediate storage. The main drawback here is that this approach doesn't scale well for large inputs due to the repeated manipulation of the string. On the other hand, the optimized stack-based approach offers a more efficient solution. By leveraging a stack, we can match parentheses and reverse substrings as we encounter closing parentheses. Characters are pushed onto the stack until a closing parenthesis is found, at which point the substring at the top of the stack is reversed and combined back. This eliminates the need for repeated string rebuilding, making it faster and more efficient. The stack-based approach has a linear time complexity of O(n), as each character in the string is processed exactly once. It also has a space complexity of O(n), to accommodate the stack used for storing characters. This approach is efficient because it avoids the repeated string manipulations that make the brute force method slow. Another alternative is the two-pass approach with index mapping. In this technique, we first pre-compute the matching indices for all parentheses using a stack. This pre-computation helps us determine which parts of the string need to be reversed during a single traversal. By using the pre-computed indices, we can reverse substrings directly without explicitly manipulating the string multiple times. This method also has a time complexity of O(n) for both the pre-computation and traversal phases and a space complexity of O(n) for storing the indices. However, its main drawback is that it involves slightly more complex implementation steps compared to the stack-based approach. The stack-based approach is the chosen strategy for this problem because it strikes a balance between simplicity and efficiency. It directly addresses the problem of handling nested parentheses by processing the innermost ones first, which is a natural fit for the stack's last-in, first-out behavior. The stack allows us to accumulate characters and reverse them on the fly when a closing parenthesis is encountered. This eliminates the need for additional traversals or string reconstruction, making the solution both elegant and efficient. The key insights here are that processing the innermost parentheses first is essential for correct reversal, and the stack provides a straightforward way to achieve that. Additionally, the stack's ability to handle characters incrementally means we avoid the overhead associated with alternative approaches, such as pre-computing indices or repeatedly rebuilding the string. This simplicity in implementation also makes the stack-based approach easier to debug and understand. When comparing the different approaches, we see clear trade-offs. The brute force method, while conceptually easy to understand, is inefficient due to the repeated manipulation and reconstruction of the string. In contrast, the stack-based approach avoids this inefficiency by directly handling characters and reversals as we process the string. While the index mapping approach is also efficient in terms of time and space complexity, it involves additional pre-computation, which can make the implementation less intuitive. Overall, the stack-based approach stands out for its simplicity, efficiency, and alignment with the problem's structure. By leveraging the natural behavior of stacks, we can solve the problem in an elegant and straightforward way, making it the most practical choice for this challenge. To tackle this problem of reversing substrings enclosed within parentheses, we need a structured approach. The goal is to reverse the substrings within each pair of parentheses and remove the parentheses themselves, repeating the process until no parentheses remain in the string. To achieve this, we start by parsing the string with a stack. The stack helps us keep track of the indices of opening parentheses. Why use a stack? It's because of its last-in, first-out principle, which is perfect for handling nested structures like parentheses. As we traverse the string, whenever we encounter an opening parenthesis, we simply push its index onto the stack. When we encounter a closing parenthesis, we pop the most recent opening parenthesis index from the stack. This gives us the range of the substring that needs to be reversed. Using string slicing, we reverse the characters between these indices and update the string accordingly. After reversing the substring, we remove the opening and closing parentheses from the string. This ensures that the string is cleaned up and ready for further processing. The next step is to repeat this process iteratively. We continue traversing the string, looking for any remaining pairs of parentheses. Each time we find a pair, we reverse the substring inside and remove the parentheses. This loop continues until the string no longer contains any parentheses. At that point, the string has been fully processed, and we can return the final result. Throughout this process, the stack is the core data structure that allows us to handle the nested or disjoint parentheses efficiently. By storing the indices of opening parentheses and retrieving them in the correct order, the stack ensures that the algorithm remains simple and effective. The key insight here is that by using a stack, we always process the innermost parentheses first. This ensures that nested substrings are handled without interfering with their outer layers. Directly updating the string after reversing each substring helps the algorithm progress step by step, maintaining clarity and simplicity. Regarding complexity, the algorithm traverses the string once, performing operations like pushing to and popping from the stack, which are O(1). This results in an overall time complexity of O(n). Reversing substrings introduces a minor overhead, but it remains efficient due to string slicing. It's also important to handle edge cases. For example, if the string is empty, we simply return an empty string. If there are no parentheses, the string is returned as is. Nested parentheses require careful processing to ensure the innermost layers are addressed first, and multiple disjoint groups of parentheses are processed independently. These considerations ensure the algorithm is robust and handles all scenarios effectively. This code implements the solution to LeetCode problem number 1190, reverse substrings between each pair of parentheses. The algorithm uses a stack to process the input string. The stack allows us to handle nested parentheses efficiently. As we iterate through the string, we push characters onto the stack. When we encounter a closing parenthesis, 1. We pop characters off the stack until we reach an opening parenthesis. This collects the substring to be reversed. 2. The is removed from the stack, and the reversed substring is added back to the stack. This ensures that substrings are reversed in the correct order, including those within nested parentheses. Finally, when the iteration is complete, the stack contains the process string with all parentheses removed and substrings reversed. We join the stack elements to form the result. The algorithm has a time complexity of O(n), since each character is pushed and popped from the stack at most once. The space complexity is also O(n), due to the stack usage. This implementation is concise and handles edge cases such as empty strings or strings without parentheses effectively. Here, we start by importing the necessary utility classes and defining our solution class and method. The method reverse parentheses takes a string s as input. We initialize a stack of characters, which will be used to process the string. Then, we iterate through each character in s using a for each loop. If the current character is a closing parenthesis, we pop characters from the stack until we find the corresponding opening parenthesis. These popped characters are stored in a temporary list so we can reverse them later. Once the opening parenthesis is found, it is removed from the stack, and the reversed characters are pushed back onto the stack. If the current character is not a closing parenthesis, we simply push it onto the stack, including any opening parentheses. This way, the stack dynamically processes the input string, handling each pair of parentheses as we encounter them. After processing all the characters in the input string, the stack contains the remaining characters in their correct order. To construct the final result, we create a string builder and append each character from the stack to it. This ensures that the string is built in the correct sequence. Finally, we convert the string builder to a string and return it as the result. This approach efficiently handles the reversal of substrings within parentheses using a stack, maintaining a time complexity of O(n), where n is the length of the input string. To solve the problem, we start by initializing an empty stack, which will help us track characters and parentheses as we process the string. First, we encounter the opening parenthesis, so we push it onto the stack. Then, as we process the characters A, B, C, and D, we push each one onto the stack. When we reach the closing parenthesis, we know it's time to reverse the substring inside the parentheses. To do this, we pop characters from the stack until we find the opening parenthesis. The popped characters, which are D, C, B, and A, are stored temporarily and then reversed. After removing the opening parenthesis, we extend the stack with the reversed characters. Finally, joining all the elements in the stack gives the result ba. Here, the input string includes characters outside the parentheses, so we start by pushing A onto the stack. When we encounter the opening parenthesis, we push it as well, followed by the characters B and C. Upon reaching the closing parenthesis, we reverse the substring within. We pop C and B into a temporary list, then remove the opening parenthesis. After reversing the temporary list, we extend the stack with the reversed characters. The stack now holds a C and B. Next, we process the remaining characters D and E by pushing them onto the stack. Finally, joining the elements in the stack results in act E. In this example, we deal with nested parentheses. Starting with an empty stack, we push the first opening parenthesis and then the character U. When we encounter another opening parenthesis, we push it as well, followed by the characters L, O, V, and E. At the closing parenthesis, we reverse the substring within by popping E, V, O, and L into a temporary list, removing the opening parenthesis, and extending the stack with the reversed characters. The stack now holds U, E, V, O, L. Next, we process I by pushing it onto the stack. When we reach the final closing parenthesis, we reverse the entire substring. This involves popping I, L, O, V, E, and U into a temporary list, removing the opening parenthesis, and extending the stack with the reversed substring. Joining the stack gives the final result ELOView. To analyze the time complexity, we start by considering the main operations in the algorithm. First, the outer loop iterates through each character of the input string. If the string has a length of n, this loop runs in n time since each character is processed exactly once. Now, when a closing parenthesis is encountered during the loop, the algorithm reverses the substring between the parentheses. This involves popping and appending characters to the stack until the opening parenthesis is found. While this step might seem costly, it processes each character exactly once, pushing and popping it from the stack only once throughout the algorithm. As a result, even in cases with nested substrings, the total contribution of these operations is still n for the entire string. Next, after the loop completes, the algorithm uses the join operation to concatenate all characters in the stack into the final result string. This operation takes n time because it processes each character in the stack once to construct the final string. Combining all these steps, the total time complexity of the algorithm includes the n for the outer loop, the n for processing characters between parentheses, and the n for the join operation. Adding these together, the overall time complexity becomes n. Now let's discuss the space complexity. The algorithm uses a stack to store characters and reversed substrings. In the worst case, all n characters of the input string are added to the stack, which requires n space. Additionally, during the processing of closing parentheses, a temporary array is used to store characters between the parentheses before they are reversed. The size of this temporary array depends on the length of the substring being reversed, but it is at most n in the worst case. Since the temporary array is cleared after each reversal, it doesn't contribute additional asymptotic space usage. Finally, the result string created using the join operation takes n space as well, since it contains all the characters of the input string. Combining these, the total space complexity is n plus n plus n, which simplifies to n. We can analyze the algorithm for the best, average, and worst cases. In the best case, where the input string contains no parentheses, such as s equals abc, the stack simply accumulates all the characters, and no reversals are performed. The time complexity remains n, because of the traversal and join operation, and the space complexity is also n, for the stack and the result string. In the average case, for a typical string with balanced parentheses, each character is processed at most twice, once when it is pushed onto the stack and once when it is popped off. This results in the same n time complexity, and the space complexity remains n. Even in the worst case, such as deeply nested parentheses like s equals abc, the algorithm processes each character no more than twice. Therefore, the time complexity is still n, and the space complexity remains n, due to the stack and result string. To highlight the efficiency of the stack-based approach, let's compare it to a brute force method. A naive approach might repeatedly locate the innermost parentheses, reverse the corresponding substring, and reconstruct the string. This would involve scanning the string multiple times, resulting in a time complexity of n squared. In contrast, the stack-based solution processes the string in a single pass, achieving an optimal time complexity of n. As for space usage, while the brute force method may avoid the need for a stack, it incurs significant time overhead. On the other hand, the stack-based approach uses n additional space, which is a reasonable trade-off for the linear time complexity. In summary, the stack-based solution offers a clear advantage with n time complexity and manageable n space complexity, making it an efficient and practical choice for this problem. When working on this problem, there are a few common pitfalls to be aware of. First, nested parentheses can often throw candidates off. For instance, given an input like A, B, C, D, the inner substring BC must be reversed first before considering the larger expression. Skipping this step leads to incorrect results, so always ensure you handle the most deeply nested parentheses first. Next, the use of a stack is critical for properly managing the hierarchy of parentheses. Without it, the logic can become overly complex and prone to errors, especially with nested structures. Another frequent error is neglecting edge cases. Inputs like an empty string or strings without any parentheses at all might seem trivial, but failing to account for them can lead to runtime issues. Additionally, trying to modify the string in place while iterating through it can result in index problems and incorrect results. Instead, a stack can help you build intermediate results that can be safely reassembled later. Lastly, be mindful of inefficiencies in your implementation. For example, repeatedly concatenating strings within a loop can lead to poor performance due to quadratic time complexity. Using a list to accumulate characters and joining them at the end is a much more efficient approach. This problem is a great opportunity to demonstrate your ability to recognize common patterns. For instance, stack-based processing and substring manipulation are key elements here, and being able to identify these patterns early can make your solution more efficient. Since nested parentheses are involved, thinking recursively can also be helpful. While most candidates stick to iterative solutions with stacks, discussing recursion can showcase a deeper understanding of the problem. Interviewers often appreciate when you explore trade-offs like this. Another important topic to consider is space optimization. While stack-based solutions are standard, you might be asked to find ways to reduce space usage, such as exploring in-place processing. Finally, edge case testing is crucial. Examples include empty strings, strings with only one character, or those without any parentheses at all. By proactively addressing these cases, you can demonstrate that you think critically and comprehensively about your solution. This problem shares similarities with several other LeetCode challenges that are worth exploring. For example, problem 394, decode string, also involves nested structures and stack-based decoding, making it a great parallel. Problem 20, valid parentheses, is a simpler scenario focusing on validating parentheses, which can serve as a good foundation. Problem 856, score of parentheses, introduces another stack or counting-based approach to evaluate parentheses. Lastly, problem 22, generate parentheses, flips the problem around by asking you to construct all valid configurations of parentheses. Beyond related problems, there are alternative approaches to consider here. A recursive strategy, for example, tackles the problem by focusing on processing inner parentheses first. This method can feel more intuitive for some but comes with limitations, such as the risk of stack overflow in cases with very deep nesting. Alternatively, a two-pass string manipulation approach is another option. The first pass identifies and reverses substrings within parentheses, while the second pass rebuilds the final string. While this avoids explicit stack usage, it might require additional memory in multiple passes, which could impact efficiency. Each approach comes with its own trade-offs, so it's important to weigh them based on the problem constraints. Thanks for joining me in this walkthrough of problem number 1190. We explored the solution step by step, discussed the importance of the stack data structure, and highlighted key considerations for similar problems. If you enjoyed this, make sure to like, share, and subscribe for more. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!